study in the textbook, and that is the integral test. So the integral test is a method for determining convergence or divergence of a series. To use the integral test, there are some conditions that must be true. So, to use the integral test, f of x of the series must be positive, continuous, and decreasing. Yeah, that's it. That's all the conditions. So if these conditions are met, then basically what you do is you take the integral of the series. So like so. And if this results in an actual number, then the series converges. If this results, if you take the integral and you get, say, infinity, then the series diverges. So an important thing to note about the integral test is that it does not give you the value of the series. All it tells you is whether or not it converges. So just because you've reached a number at the end of taking the integral, that doesn't mean that this number is the sum of the series. This is just an indication of whether or not the series converges. And so I'm going to pass it off to Victoria to do an example with the integral test. Cool.
Since we're tasked with finding if this series converges, we're just going to find the integral of this expression as if it were like an equation.
So the limits of integration are what they already gave us. It's from 0 to infinity. And then we're finding it from 3 over 4 plus 7x. I'm just replacing that in with an x. And then we're just going to do the limit as t approaches infinity of this from 0 to t of 3 over 4 plus 7x dx. And then we're just going to find the integral of this. Technically, you use u substitution here. And then you would get that the limit from t to infinity is just this whole integral from 0 to t times 3 over 7, and then we would have our 1 over u du. And then we will have our limit from t to infinity of 3 over 7 times ln of u. And then we would just put back in u to our equation. So we will have the limit from t to infinity of 3/7, and this goes to natural log of 4 plus 7x. And then technically our x is infinity here. So this ln would just be going to infinity. And since it goes to infinity, the series diverges instead of converges.
So for a second example of the integral test, we are asked to determine whether the following series diverges or converges. And so in order to know whether or not we are even able to use the integral test, we check that the series is positive, continuous, and decreasing on the given interval, which it is, and so we move forward with the integral test. So the first step we're going to do is to rewrite our series in the form of an improper integral, and so this becomes the integral from 1 to infinity of 2 over x squared plus 6x plus 10 dx. And so this can also be rewritten as us taking the limit of from t, as t goes to infinity, of 2, or the integral of 2 over x squared plus 6x plus 10 dx. this integral becomes simpler to solve when we rewrite it as limit as t goes to infinity. Here, 1 to infinity of 2 over x plus 3 all squared plus 1 dx. And so we see that we have a 2 here, which we can remove out of the integral, and so this can also be rewritten as the limit as t goes to infinity of the integral from 1 to infinity. We bring out our 2, and it becomes 1 over x plus 3 all squared plus 1 dx. And so we can notice that this integral here is actually the solution for it would be arctan of x, and so this becomes the limit as t goes to infinity for 2, and then we have arctan of what is in our bracket, which is x plus 3, and we're taking it from 1 to t, which is infinity. And so this now becomes the limit as t goes to infinity of 2 arctan of, we're going to bring in our t and substitute it into the integral, and so it is t plus 3, and then it's going to be minus arc, or rather 2 arctan of, we bring in our 1, and it's 1 plus 3 becomes 4. So this becomes, when we substitute infinity here, it becomes 2 arctan of infinity, and we know that this goes to pi upon 2, and so this is 2 here times pi upon 2, and then minus, we leave this as it is, and it's 2 arctan of 4, and so this is a constant, and so we know that our series converges.
So we will now be covering 11.4, the direct comparison test and the limit test. So foundationally, the direct comparison test and the limit test exist to evaluate the convergence or divergence of a complex series whilst comparing it to a series of a similar form that is already known to either converge or diverge. So simple series with known convergence or divergence fall into 2 primary categories. We have the p-series and the geometric series. So the p-series follow the form the sum of 1 over n to the p. So the series converges if the exponent p is greater than 1, and the series diverges if the exponent p is less than or equal to 1. Now, for geometric series, they follow the form of the sum of a r to the n minus 1. Now, the series converges if the absolute value of r is less than 1. And the series diverges if the absolute value of r is greater than or equal to 1. With these simple series in mind, we move on to the direct comparison test. So the direct comparison test assumes a complex positive series that we can call a to the n, and I'll write here that it's complex. Complex meaning that on first glance it isn't evaluable, and we have to bring a simple series, or we are provided with a simple series to evaluate the convergence or divergence of the series. So we have our complex positive series a subscript n, and a positive simple series, which can either be, as previously mentioned, geometric or p, will be written as b subscript n. So if the simple series b subscript n is convergent, so if b of n is convergent or converges, and the complex series is less than or equal to the simple series, then the complex series is also convergent. And if b subscript n, or the simple series, is divergent, and the complex series a subscript n is greater than or equal to the simple series, then the complex series is also divergent.
So we will be putting the direct comparison test into practice with this series. So here we can take the simple series and determine its convergence. And if we recall our previous knowledge of p-series, this is a recognizable p-series. And because we've encountered it before, we know that if p is more than 1, that the series converges. And if p is less than or equal to 1, the series diverges. So here, p is 6, so we know that the series, or at least simple series, converges. And also from looking at the two series, we know that the left is smaller than the right. And so given the fact that we know that this is the lesser series from this one, when we apply the direct comparison test, we know that the series in general converges as well.
What if the complex series doesn't have either relationships listed to the simple series? What if the simple series is convergent, but the terms of the complex series are larger? Or what if the simple series is divergent, but the terms of the complex series are smaller? This is precisely where the limit test comes in. In these cases, the limit test guides you to divide the complex series, a sub n, by the simple series that we're calling b sub n, and to take the limit as n approaches infinity. So limit as n approaches infinity of a sub n over b sub n. Through this, if you result in a finite number that is greater than 0, so let's call the finite number c, and c is greater than 0, then both series either converge or diverge, as analyzable by the simple series. And we employ these tests, both the direct comparison and the limit test, only if both the series are positive. Their utility is to analyze the convergence or divergence of a complex series.
So we are going to determine whether the p-series diverges or converges using the limit comparison test. So we have this series, which is pretty complex, so we're going to use a simple series to do this. We're going to use a pretty common series that you've probably seen before, probably 3 minutes ago or something. I'm just going to draw it out really quick. This is a p-series that has a p-value of 1. We're going to write that down really quick. And as we know, p-series where the p-value is less than or equal to 1 diverge. So this one diverges. Okay. So we're going to use, again, the limit comparison test. So I'm just going to find the limit as n approaches infinity of
a sub n over b sub n.
We're gonna let this one be a sub n, and this simple series will be b sub n. So let's just quickly do that. Minus n and 4 plus 5. And divided by b times b sub n. I'm just gonna write it like this. But, that will be like that basically. I forgot to write the little limit here, but it's okay, we're gonna rewrite it anyway. So we're gonna be finding the limit as n approaches infinity of 2n to the 4th minus n cubed over n to the 4th plus 5. So we're just going to evaluate that limit. So we're going to end up with, there is a common factor of n to the 4th in the numerator and denominator, so that's why we're going to factor it out. And we're going to end up with this limit. Minus squared and 1 plus 5 over n to the 4th. This will turn out to be 2 minus 0 over 1 plus 0. And we're going to get a constant of 2. And because it is a constant, that means that this diverges. And both this and the simple series diverge.